So I'm getting my YouTube channel going again. This is the first video I'm going to do. I'm going to talk about hybridization, but I'm not going to do what everybody else does. The focus is on not this process that we follow. I'll go through that. The process is the focus is what it all means. So let's start with our standard approach. We're looking at methane. I've got two representations for this on the board, and you'll see why that is in a moment. We've got our electronic configuration 1s2, 2s2, 2p2, and in our standard explanation of hybridization we promote an electron from an s orbital to a p orbital, so we get 1s2, which we're going to ignore, 2s1, 2p1, well, let's call that the x, 2py1, 2pz1, I'm running out of space. And then what we do, this is the bit that we call hybridization. We mix these four orbitals up and we call it 2sp3 4. We say that instead of having our four individual orbitals, we're going to mix them all up and split them again. And you'll see on some videos and you'll read in some textbooks that methane forms stronger bonds with hybridized orbitals. The hybridized orbitals allow carbon to form stronger bonds to hybridization. You'll see that. It's absolutely categorically wrong. What I'll show you in a minute is the canonical molecular orbitals of methane, and I'll show you how they form bonds. So what we have in methane is our carbon atom with its four outer electrons, and we have our hydrogen 1s1. We've got four of those, so we get four more electrons. We can fill all of these orbitals so that it's 2s2, 2px2, 2py2, 2pz2. Carbon has an octet, and we don't need to do any hybridization to see what those orbitals look like. So I'm going to show you, I'm going to sketch them. I could show you some fancy computational chemistry diagrams, and you'll find those in various resources, including at some point my research publications, and certainly in one of my textbooks. So we've got an s orbital on carbon, and it has spherical symmetry. So what we have is a big blob of probability, places where you might find an electron. And that diagram's not much use. Let's look at a p orbital now. And what I'm going to do is arbitrarily define this as the z-axis. So what we have with our p orbital is something that looks like that. And then we know that a p orbital has a node. So on the other side of the carbon atom we have something that looks like this. And this is what I'm representing here is a molecular orbital. So far this looks like an atomic orbital, but we want the molecular orbital that's derived from this overlapping with our s orbital on carbon with the correct symmetry. And we can do this here. Remember, this is a wedge, so this is coming out of the board, and we've also got a dashed bond going into the board. So now we've got to focus on what hybridization actually is. Hybridization is something we do mathematically on the orbitals. We don't ever have a situation where a carbon atom comes along with four outer electrons and somehow we actually physically promote an electron from one orbital to another, and then it forms these hybridized bonds. That is never something that happens. But what we can do is we can take a bit of this orbital and a corresponding bit of this orbital, and so this is the, I think I said X and then I've labelled it Z. Okay, it doesn't matter, one of the axes. Now we've got our p orbital here, but we've also got p orbitals at 90 degrees to it. So if we look at the way I've drawn the methane, then you'll have an axis going that way and another axis going that way, and we could rotate, we could label these hydrogen atoms A, B, C and D. We could rotate this methane around and we could draw exactly the same thing with any other pair of hydrogens. If we pick this as our reference point, we could draw the same thing. So we've got it, this one with this one in effect. We're going to have another orbital with this one and another orbital with this one, and the same applies to every combination. So we've got one of these, and we've got three of these. So that's where our sp3 bit comes from. But all we're really doing is we're taking, let's call it a quarter. We're taking a quarter of this orbital, we're taking a quarter of this orbital, and we're taking a quarter of the other two p orbital molecular orbitals. We're chopping those out and we're combining them. That is mathematically acceptable because this molecular orbital is a solution to the Schrödinger equation, the mathematical function that defines this orbital. If we chop a bit out of it, and another bit, and another bit, and another bit, if we were to add those up, a linear combination of those wave functions, each individual bit would be a solution to the Schrödinger equation. So taking a quarter of this is valid, as is taking a quarter of this. And then adding this bit to this bit, and this bit to this bit, and so on, is also valid. So what we can do purely mathematically, there is no physical process going on here, is we can generate some more orbitals, and here's why we do it. You want to use curly arrows to draw a reaction mechanism. You start a curly arrow at a bond. You want to think about that bond, that line, any of these lines. It's really, really convenient to think about having 2 electrons in that bond, and 2 electrons in that bond, and 2 here and 2 here. As a net effect from these orbitals, it is true. We have 2 electrons in this orbital, so in effect half an electron on average is in this bond, and half an electron from this orbital and half an electron from each of the other 2 orbitals, and 4 of those halves adds up to 2. That's an average, but we don't get this with these canonical molecular orbitals. So we're borrowing a quarter of each of these orbitals, and that's for convenience. It's because it allows us to talk about the bond. It is absolutely not real. So if I draw an energy level diagram for my carbon and then 3 p orbitals, and I populate that with my 8 electrons in total, and these are now getting 1 electron from each hydrogen. It's just the same. So the bonds to each individual hydrogen, the net amount of bonding is exactly the same whether we use the canonical orbitals or whether we somehow take the average of these s and 3p orbitals and then partition them among the CH bonds to give these new molecular orbitals that we can still use. They are just as valid as solutions to the Schrödinger equation, but they have no physical reality. So it's really important to me that everybody understands not what hybridization is. I think you need to understand the conceptual process, this idea of promoting an electron and then mixing them up. But what I wanted to do is show you what that mixing would look like, and then we get something for one of these hybridized orbitals in methane, where we have a probability of finding an electron, but we also have the bit that doesn't come out of this is the bit that comes out of the maths, the quantum mechanics, is we're not just borrowing a bit of this, we're also borrowing a little bit from over here at the same time. So we get this type of sp3 hybrid orbital. As I say, I'll say that again. That symmetry, that full picture, doesn't come out of the visual representation that I've just tried to show you about what we do with hybridization. So you do need to do some quantum mechanics here, and there are lots of computer programs that will allow you to calculate orbitals, and every organic chemistry textbook has a picture that looks something like this. And this is kind of important when we start looking at antibonding orbitals, where this lobe is bigger than this one. So it's all part of a bigger picture. So when we start talking about hybridized orbitals overlapping, well, here this is one orbital overlapping across 5 atoms. It's a 5-center 2-electron bond, and this is perfectly normal. Molecular orbitals, pretty much by definition, span the entire molecule. And once you shift your viewpoint, well, things do get a bit easier. Okay, so that's a short video which is a slightly different perspective on hybridization. So have a look at loads of other videos on hybridization that show you how to go through the process. I want to give you that extra bit. It's not real, but still learn it because it's useful. Just have a deeper understanding of it.